Hi, IB. This is just a quick recap of what 15b is all about with the chain rule. So just think about the word chain as linking, and we are going to link an inside function with an outside function, which we called a composite function several chapters ago back in your functions unit. And what we just want to look back at right now is identifying what the input or what would affect the domain versus what would affect the range. And we have a composite function here. We have 2x plus 1 as kind of your inside function. And that 2x plus 1 is being substituted into something squared. So we're going to identify this inside function as your u. So therefore, your u is being squared. And we can say your u is the 2x plus 1 part. If you were thinking of two functions that we were using a lot of g and f when we were doing composition. So we could say that g of x is x squared, and f of x is 2x plus 1. So therefore, if you thought about how we would compose f of g of x, so if we did f of g of x, we would wind up putting g into f. So that would mean we would have 2, and then x squared would be substituted in to this x plus 1. Or if we were finding g of f of x, we would put f into g. And therefore, we would take something squared, because that's the skeleton of what g looks like, and then we would put the 2x plus 1 inside of g. So just remembering that we can identify an inside and an outside function. So if we were going to take the derivative of a function like this, right now we would have to expand, because we only know the power rule, where we wind up multiplying the exponent by the coefficient. So we need kind of a polynomial. We need a long string of terms in order to take the derivative at the moment. So if we wound up expanding this, we would wind up with 4x squared plus 4x plus 1. And then we could take the derivative or do something else with it. But at the moment, we'd have to expand. So let's see if the chain rule can help us speed up this process a little bit. So what the chain rule winds up telling us is that if we have a function y, and we can write it as the function g of u, where u is another function f, we can basically take the derivative of y, so we can find y prime or dy with respect to x, since that is your input, by taking the derivative of y with respect to u first, and then the derivative of u with respect to x first. So there's the composition. So even though we're taking the derivative of y with respect to x, we have to go through this u first, because we have an inside and an outside function. All right. Another way of seeing that is if you have a function raised to a power, we'll use the power rule again. However, instead of just having x as your function, where the derivative is 1, we actually have a separate function where the derivative might not be 1. So we would have to use the power rule. So our exponent would multiply by our coefficient. We would drop 1 degree, but then we would have to also multiply by the derivative of whatever the inside function is. All right, so we're going to wind up looking at a few examples to see how this actually looks when we apply it. So our first example, we'll notice that we have an inside function. So we can say that our u is x cubed plus 2x. All right, and our y is just something being squared. So when we take the derivative, we wind up saying that 2 multiplies by the coefficient. So we wind up with 2. We keep our inside function. We drop 1 degree, and we'll keep our inside function as it is. However, we'll then multiply by the derivative of the inside function, which is going to be our u prime. So 3x squared plus 2, and that's what we'll wind up multiplying by. All right, and we have the derivative right now. Of course, we could expand this and simplify it a bit, but this at this point, this is your derivative. So if we did this again, let's say we take f prime or f dashed. Again, we notice that something is being raised to the 6th power. So we wind up saying, okay, let's call this u. So the derivative is going to be 6 times our u to the 5th power. So we keep u the same, 1 minus 2x, but then we have to multiply by the derivative of u. So again, if we identify u as 1 minus 2x, then u dashed would wind up just being negative 2. This one's really nice to clean up. So negative 12 1 minus 2x. We're not going to expand this to the 5th power, so we would leave it as is. But negative 12, at least we can simplify that a bit. And even with this one, actually, we could at least distribute the 2 to either one. I'll leave that one as is, but you guys might notice that if you check in the back of the book, it might be written in a little different form, and we always want you guys to simplify as much as you can correctly. I would say with a power of 1 or 2, you could probably expand and simplify. If it's anything larger than that, then you can leave it in factored form. For this third example, we have to do a little bit of work before we actually begin to take the derivative. So I'm still going to call this y because it's not the derivative yet. But what we notice is that we have a square root in the denominator, and I want it to be brought up to the numerator, just like we were doing with our simpler expressions last week, with our 15a as well. So 6, I'm going to bring this up. So 2x squared minus 3x is raised to the 1/2 power, but negative 1/2 because it's in the denominator. So now I can identify this as 6u to the negative 1/2 power. So we can let u be the 2x squared minus 3x. Once I have it written like this, I can go ahead and take the derivative. Because negative 1/2 times 6 would be negative 3, I keep my inside function the same. I drop 1, so negative 1/2 minus 1 is going to be negative 3/2. And now I can multiply by the derivative of the inside function. So that would be 4x minus 3. We never want to leave negative indices, so let's at least try to clean this up. The 3, negative 3, and the 4x minus 3 will stay in the numerator. So I'm going to wind up expanding that to be negative 12x and then positive 9. And my denominator will be the square root of 2x squared minus 3x raised to the 3rd power. So remember, the denominator of a rational index is your root, and the numerator is your power. So the 2 technically is here. The negative tells us we're in the denominator, and then the negative 3 times the 4x is negative 12x. Negative 3 times negative 3 makes the positive 9. So this is your derivative written in the best form to leave it in. All right, guys, so those are 3 examples of the chain rule. Go ahead and try some on your own, and we'll be ready for product and quotient rule coming up next. Have a good night.